we're going to continue on now talking about singular perturbation theory, and in particular its relationship to boundary value problems. And one of the things I want to highlight in this lecture, what's called dominant balance or distinguished limits and matched asymptotics. So all of these play this key role in understanding how we want to do perturbation theory for these singularly perturbed boundary value problems. And this concept of dominant balance or distinguished limits is actually a broader concept that we will start to engage with throughout the rest of lectures, because what it's really highlighting for you is that in many systems, in different regimes, whether it's dynamic regimes or in spatial regimes for boundary layer theory, you can have dominant physics that is different than in other parts of your domain or different parts of time. And so this concept is really important to understand, and we're going to walk it through with one of the classic problems out of boundary value problems. Okay? So I want to consider this. This is sort of your canonical problem to start understanding these issues, which is the following singular problem. It's a second order linear differential equation. The epsilon is in front of the highest derivative, where we know the problem is, because if you take epsilon to 0, this drops out. You get a first order equation that has one solution with one constant, and it cannot satisfy both boundary conditions. Okay? So the epsilon is what creates this problem because it's in front of the highest derivative. Now b of x, c of x are just some functions that are prescribed in the problem. For at least the first part of this, we're going to think about b of x either being positive or negative on the whole domain, and that's actually the one parameter that's going to be important for us to consider in a little bit is what is this parameter? Is it positive or negative? So I want to start to understand this problem by breaking it into the pieces we talked about last time, which is to say we want to think about what the outer solution is, what the inner solution is, and also this matching region where the two solutions are together. So let's talk about the outer problem first. The outer problem is just the simple application of regular perturbation theory. In other words, just take the solution and expand in epsilon. Okay? So u is equal to u naught plus epsilon u1, plug it in, and what you find is the following. At order 1, here's your first order differential equation. At order epsilon, here's your first order differential equation, but now on the right hand side, it's forced by u naught xx. Okay? So that's just regular perturbation theory, and right away you can see that a first order equation can only satisfy one of the boundary conditions. So right away I have a problem, and of course that's exactly why we have the outer solution. The real question comes though is where is the boundary layer? So part of the thing we want to address is exactly that issue. Is before, in the previous example, I said, well, the boundary layer was at x equals 0, but I'd really like to understand where it is first, because this problem can satisfy one of the boundary conditions, but not both. So which one should it satisfy? So the solution itself is given by here. So if I solve the leading order problem, I can just divide by b of x, and let's again say b of x will either be positive or negative on the whole interval, so I can divide by it, and then I can solve this by just simple integration. So there's my solution. This is the solution. There's my unknown constant c. So I have one constant to play with, and that constant has to satisfy my boundary condition. But I don't know if I'm satisfying the boundary condition on the right or on the left. We have to determine how to understand where to get that information. The inner problem is really thinking about some region of the domain where the dominant balance is different. So I'm going to do a rescaling of the equations into a new variable that's going to stretch out this boundary layer region. So if I believe there's a boundary layer, I want to take this region of rapid transition, and then I want to write it in terms of a new variable where this rapid region, which is very thin in space, gets stretched out. So that is done by something like this. So for instance, this is the stretching variable, c, if I stretch it around x equals to 0. So x over delta. Okay? So I did this before, and I really want to spend some time talking about this delta, because delta is going to be another small parameter that I have in the problem to go along with epsilon. So the question is, what's the relationship between delta and epsilon? And what I did, so this is going to be the whole goal of this work, is to start to determine what's called the dominant balance in order for us to get self-consistent equations. So we're going to talk about this. So if I plug this in, just plug it into my governing equations, then I have u of x. Here's the chain rule, is u of c of x, which is 1 over delta u of c. And uxx now becomes 1 over delta squared u c. And if I put this into my rescaled equations near this boundary layer, here is what I end up getting. I get epsilon over delta squared, second derivative. I have b over delta, first derivative, and then c times u. And again, b and c are now valued in this inner variable. So the real question comes is, how should I pick this delta in relationship to epsilon? They're both supposed to be small, but it could be that epsilon is much smaller than delta, or delta is much smaller than epsilon, or epsilon and delta are about the same size. These are called different distinguished limits. And ahead of the time, you don't know how to pick that. And part of your goal in doing this singular perturbation theory is to understand, how do I pick the delta and epsilon relationship? Okay? It's not as simple as just simply saying delta is equal to epsilon, because there's many cases when that is in fact not the case. So let's look at some of these distinguishing limits. So distinguished limit number 1. Epsilon's just bigger than delta. So remember, delta and epsilon are both small, but even within this small world, epsilon's much bigger than delta. So what does this mean? Well, let's go back to our equations. If epsilon, so epsilon's much bigger than delta, right? So if you look at what you have here, this is going to be divided by a delta squared. So if delta is really much smaller than everything, this 1 over delta squared is going to make this term here bigger than everything else in here. In fact, if you compare these two terms, right, this has a 1 over delta squared. This is going to be much, much bigger because delta is so small, and it's way bigger than that term there. So this term here is going to dominate over the others. Right? So when you do an expansion, there's only one term that matters. It would be this one. That's the leading order term if you take this distinguishing limit. And so you'd have this. uxc is equal to 0. So that's the distinguished limit that comes, the leading order behavior that comes in this limit. Epsilon is much bigger than delta. So what are the consequences of that? Well, the consequence of that is that, well, the solution then in this inner region with that kind of expansion is just this linear, just integrate twice, you get some constant times c plus e. So pretty easy to solve, and that's what you would get in this distinguished limit, except there's a problem. In this limit, what we know we have to do is, when I'm in this limit, what I want to do is do the matching eventually, which is I want to take the limit as c goes to infinity in this new variable, right? And I want to match it with my outer solution. So let's go ahead and do that. Take c goes to infinity of the inner solution. And when I take c goes to infinity, it means I should go out and match my outer solution. But when I take the limit c goes to infinity, notice what I get. This thing blows up. Okay? So that's problematic. So I don't want the solutions to be going to infinity. So I'm going to rule this out as the distinguishing limit. I'm going to say that is a possibility. That's one. And it creates this problem, and so I don't want to use this one. What about this distinguishing limit? What if epsilon is much smaller than delta? Well, in that case, you can go back to your original problem and say, well, if epsilon's a lot smaller than delta, then what you end up with is this differential equation. So the second derivative drops out and the constant drops out. This is the dominant term. Okay? So if that's the dominant term, then what kind of solutions are there? Well, uxc is equal to 0, essentially. So your solutions are just constants. Now the problem with the constant solution is that you have to satisfy with this inner solution both a boundary condition and a matching condition. So you need two parameters to do this. And here you only have a single parameter. And so basically you're going to fail to satisfy both your matching condition and your boundary condition, because you've dropped it down into a scenario where you only have the solution which is constant, and there's one free parameter, and it's incapable of matching both the boundary condition and also matching the conditions between the outer and inner solution of having them be matching each other in the asymptotic limit. So again, I would say that this distinguishing limit is also a failure. So epsilon much less c, delta is a failure. Epsilon much bigger than delta is a failure. So what's left? Well, there is this. Epsilon's about the same size as delta. Now, if you take epsilon about the same size as delta, what ends up happening then is your governing equation that you had before drops down to here. So you get, this is your leading order 2 mu x c plus some constant b u x c, and the epsilon just shows up here. So now when I expand this, my leading order solution, well, it's a second order differential equation. There it is. And here's the correction. And so now it's a second order differential equation, which is going to allow me two solutions. So I'm going to be able to get two unknown constants, one of them to satisfy the boundary, the other to satisfy the match. Let's also see what kind of behavior I get out of this. And by the way, B0, I'm going to call B0 essentially looking at B of epsilon c, which is near, it's either 0 or 1, depending if the boundary is on the left or the right. Right? So this B value is going to be take on the value of the boundary if the boundary layer is on the left or the right. So that's what the B0 is intended to represent for us. So I want to really replace that B there with B0. And then ask the question, what kind of solutions do I get? Well, if the leading order is this, here it is, then my solutions look like this. And I'm assuming here that B naught's positive. And then the solutions look like this. And notice a couple nice things. I have two coefficients, D and E. So two unknowns. I have to satisfy a boundary condition and a matching condition. And I have two conditions to do that. That's great. The other thing that happens is when c goes to infinity, what happens? Well, this thing here goes to 0. So that's also very nice. So nothing's blowing up. So this looks like a very promising limit for us to be using, or this distinguishing limit that we want to use. Okay? So epsilon is delta is going to be our distinguished limit. It's the only one that makes sense. I've already shown you that if you change the distinguished limit, you get inconsistencies in the kind of solutions you're going to get out. The last thing I have to do is think about matching. And the matching condition is I have to take the outer solution and inner solution, and they should match each other near the intersection of the boundary layer and the outer solution. Okay? So here's my inner solution. Here's my outer solution. I have the two solutions. But in order for me to do this matching, I have to figure out, is the boundary condition on the left? Is the boundary on the right? Okay? Here I've assumed that b of x is always either positive or always negative. If b of x is 0 somewhere in the domain, you can actually get an internal boundary layer. And I'll show that example in a moment. So here are the two possibilities. If the boundary layer is on the left at x equals 0, then the limit x c goes to infinity of the inner solution has to be equal to the limit of the outer solution as x goes to 0. Okay? If the boundary is on the right, so at x equals 1, then the limit x c goes to negative infinity. In other words, you have that expansion variable and you're going the opposite direction into the domain of un has to equal the limit of the outer solution at x equals to 1. So those are your two possibilities. Right now is you have a boundary layer on the left at x equals 0 or on the right at x equals 1. So let's consider two cases. And it's all related to whether b of x is positive or negative. If b of x is positive, okay, then I can ask the question, what does the outer solution look like, for instance, or the inner solution look like in these two different cases with a boundary layer being at the left or the right? So let's consider x equals to 0 first. If I look at my inner solution, here it is, x c goes to infinity, u inner solution. The solution of the inner solution is given by d e to the minus b naught c plus e. So when c goes to infinity, what happens? This here goes to 0, and this is some value e. So it's bounded. just some constant. So that's what the inner solution value goes to as c goes to infinity near x equals 0. However, at x equals to 1, if I take this area and I say, well, in this case, I'm going, on the x equals to 1, I'm going back into the boundary. So I have to go x goes to negative infinity. I take that inner solution, and I take x goes to negative infinity. And now this becomes plus e to the plus b naught infinity. This goes to infinity. So my solution blows up in this case if the boundary is x equals to 1, but it's finite if I have the boundary layer at x equals 0. So the only self-consistent thing here is that the boundary layer must be at x equals to 0. Because if it's x equal 1, I get things like this, which are unphysical. No solutions going to infinity. So b of x is positive, I get a nice solution. If b of x is negative, the opposite happens. At x equals 0, if b is negative, then if I had a boundary layer at x equals 0, my solution blows up when I compute what the inner solution is doing near that boundary. When I try to do the matching, this thing blows up. However, at x equals to 1, if I now do this expansion, I get something well behaved. So this is very nice because what it's telling me is just by knowing the sign of b of x, whether it's positive or negative, if b of x is positive, my boundary layer is at x equals to 0. b of x is negative, my boundary layer is at x equals to 1. And so instead of you trying to guess where the boundary layer is, what you're doing is saying, do I get a self-consistent solution that's not blowing up at either end? And that's exactly what we computed here. So you can determine the location of the boundary layer. Okay, not try to guess the location, but actually just this is the way to just say, where would the boundary layer occur? You have to have solutions that are finite, that don't blow up and allow you to match the outer solution. Okay, so let's take an example where b of x is positive. So b of x is positive. I know my boundary layer is going to be at x equals to 0 in this case. And if you remember then, what's going to happen now then, if my boundary layer is at x equals to 0, the outer solution then is going to satisfy the boundary condition at 1. And the inner solution will satisfy the boundary condition at 0, right? Because that's where the boundary layer is. So now that's the implications of this here is if b of x is positive, outer solution satisfies the right, inner solution satisfies the left. That's going to determine some of the coefficients in your problem. And now what we do is we produce the uniform solution by taking the inner and outer solution and subtracting the match. And so your solution, after you're doing this, is given right by here. There is the solution right there. Okay? All right. So that's the, let's call it the general theory for this second order singular boundary value problem that we have here. Not only does it highlight how we can find where the boundary layer is, but it gives us a way to approximate the uniform solution, for some generic b and c, functions b of x, c of x. Okay? So let's start looking at some examples. In particular, what I want to do is now start breaking that problem and start showing you some interesting things that can happen when you don't satisfy b of x always being positive or negative, or if b of x is 0 on the domain. So I want to first of all talk about this case when you can have multiple boundary layers. So what does this mean? Well, here's the example I want to highlight for you. There it is, epsilon u of x. It looks very similar to what I had before. My b of x is minus x squared minus u equals 0. And my domain now actually is supposed to be u of negative 1. Sorry, this is correct. U of 0 and u of 1. So b of x, notice it's negative, right? So the boundary layer, from what we just showed you, the boundary layer should be at x equals to 1. But notice at x equals to 0, it's actually 0. It's not positive. So there exists the possibility that something interesting happens at x equals 0. So our normal boundary layer predictions that we just did would say, like, well, if b of x is negative, the boundary layer is on the right, and so that would be at u equal 1. But there's something interesting that happens at x equals to 0, this is actually 0. It's not positive. So in fact, something interesting will happen there, which is we're going to get a boundary layer at 0 and at 1. Okay? So I expect a layer at x equals to 1 because the b of x is negative, except that now at x equals 0, b of x is 0. So something interesting can happen there, and in fact, it indeed does. So I'm going to rescale this. So again, we're going to come back to the dominant balance. So first what I'm going to do is I'm going to go look what happens near x equals to 0. So I want to do a dominant balance calculations near x equals to 0 by defining in a new variable c is equal to x over delta. Just like what we did before. I'm going to take the region around x equals to 0 and expand it with this new variable c, which is parameterized by delta. So when I do this rescaling, the inner variable, in terms of the inner variable, here's what my leading order solution looks like. There's an epsilon in front of here. Notice this term. This is interesting. There's a delta cubed, c squared, and minus delta squared. So first thing I want to highlight is delta and epsilon are both small. So when you look at these guys right here, there's a delta cubed and a delta squared. So this will all be smaller than this. So I'm going to throw that out over here. So then you're left with two terms. You have an epsilon here, delta cubed there. And then the question is, how am I going to go about balancing these things to make them work? So the dominant balance looks something like this. Sorry, yeah, so this is much smaller than this guy. So delta cubed is smaller than delta squared. So I throw this term out. So sorry, I said that wrong before. Delta squared and epsilon uxx. So this is the dominant balance, these two terms. And now the question is, if epsilon is, how do these two terms balance each other? Because if I pick delta to be much bigger than epsilon, much smaller than epsilon, what happens between these two terms that are supposed to be balancing? So here's what I'm going to do. In fact, I want those two terms to balance because I want to be able to generate solutions that are bounded, have two coefficients, which allow me to generate a solution that satisfies the boundary and matching. So I'm going to pick the balance, which is delta is equal to epsilon to the 1/2. And if I choose this and put that in there, notice I have a delta squared, which is epsilon to the 1/2 squared, which is epsilon. So there's an epsilon in front of here, epsilon in front of here. These two terms are of the same size. By the way, it doesn't take that much work to violate this and say, what if this doesn't hold so that this term dominates or this term dominates? And you can very easily show yourself that you get solutions that are essentially not going to allow you to do matching or satisfy the boundary conditions. This is the only balance that allows you to do it. So this is our distinguished limit. And so it tells you something very important. Your boundary layer x equals 0 has a width that's proportional to epsilon to the 1/2. Okay? Not epsilon. That's something we got last time. But now you get this interesting structure where the width scales like epsilon to the 1/2 in that distinguishing limit. Now what about on the right? Let's talk about the distinguished limit on the right. So now I know there's a boundary layer on the right. So to formally do that expansion, here's what I'm going to do. I'm going to go ahead and say c is equal to 1 minus x over delta. So notice here, I'm expanding directly around x equals to 1, which is the right boundary. So I'm going to expand around there because I want to take that x equal 1 layer and expand it out. So I do the expansion. And here's what it looks like in the inner variables. And again, I have an epsilon here. I have a delta here. I have a 1 minus, and there's a delta here. So this is going to be small comparison to 1. I have a delta squared here. Okay, so now I want to start taking the dominant balances. And notice that I have a delta squared here, and I have a term here with a delta and a 1 here. So this term here will be bigger than this term. And in order for me to balance this term with this term, I would take epsilon to be the same size as delta. And if you do that, so there you go. So this is what you get at the dominant balance. And you can say, like, I have an epsilon and a delta. To make these two terms balance in the leading order solution, take them to be epsilon is equal to delta. So that's what we're going to do. That's the distinguished limit. Again, you can convince yourself very easily if you don't have this be satisfied so that this term dominates or that term dominates, what you end up with is non-self-consistent boundary layers. You either can't satisfy the matching and the boundary or the solutions blow up. This is the only balance where you can satisfy the boundary condition, you can satisfy the matching condition, and you get finite solutions. Okay? I won't go through and convince you of all the others, but that's exactly what happens. So the leading order solution here, oh, by the way, now we're going to also talk about the outer solution. So what I just showed you is the inner solutions. In fact, you have two inner solutions. You have the inner solution on the left and the inner solution on the right. So you have two boundary layers, one with thickness epsilon, one with thickness epsilon 1/2, but then you still have your outer solution. So let's do the outer solution, which is you just take your equation without rescaling, just set epsilon to 0, and that's your leading order problem. There it is. Okay? So there is the leading order problems. First order differential equation with this x squared. The solution is given by here. You can solve for it. U naught is c e to the 1 over x. Okay, so let's go ahead and calculate the solutions for the other regions as well. The inner solution at x equals 0. Well, remember, we're going to scale with a thickness epsilon 1/2. So c is x over epsilon to the 1/2. Plug that in. Here's your leading order problem. And I didn't give you the solution last time, so I'm going to give them to you now. Your solution now is this here. A e to the minus c plus b e to the c. Pretty simple solutions. There you go. So I have an inner solution. I already got the outer solution. This is one of the inner solutions near x equals 0. Let's get the outer solution, inner solution. So by the way, before I get carried away, one of the things I'm going to want to do is I want this inner solution to satisfy the boundary condition on the right. Sorry, at x equals 0. So on the left, I want to satisfy the boundary condition. And also, I want, when I do the matching, I don't want things to blow up, which means I'm going to have to throw away that b term there. That b is going to have to be 0, because I'm going to take c goes to infinity, and this will blow up on me. So, but I'll take b equals 0, and I'll make it satisfy the left boundary condition. So a is going to be 1, and this is your solution there, e to the minus c. On the right, here is my inner solution. C is 1 minus x over epsilon. Plug it all in. Here you go, second order differential equation. It satisfies the right boundary condition. There it is. U0, 1 is 1. You can easily solve this as well. And there's your solution. And this solution, notice it satisfies the right boundary condition. And then later we're going to match it. So I have one unknown parameter left that I'm going to find out when I try to do matching. Okay? All right, so let's go about and try to match things now. So matching now has to occur at both sides, x equals 0 and x equals to 1. And so let's go ahead and do the matching. So here's how the matching works. At x equals to 0, you take your outer solution and match it to the inner solution on the left as c goes to infinity. At x equals to 1, you take the outer solution going to 1, and you match it against the inner solution going x goes to infinity. Remember, I did my inner variable c was 1 minus x over epsilon. And so when c goes to plus infinity, that means you're moving into the domain where the outer solution lives. Those are the matching conditions. And you can apply them. And what you end up with then is your solution, your uniform solution, is the outer solution plus the two inner solutions minus the two matches. Okay? So before I just had the outer solution plus inner solution minus the match. Now I have the outer solution, the two inner regions minus the two matches, and this is the uniform solution you get after doing your work. So there you go. I have the solution, and it has two boundary layers. Notice I have my solution here, e to the x over square root epsilon, and an e to the 1 minus x over epsilon. So if you look at that, here's what this thing looks like. You get a double boundary layer structure. On the left, here is the boundary layer with thickness epsilon 1/2. On the right, is the boundary layer with thickness epsilon. And what I've shown you here is a variety of solutions as a function of epsilon. And the gray region just shows you sort of the inner region of the left boundary layer and the right boundary layer. And they're different thicknesses. But you can see rapid transition happens here. Then you have the outer solution, rapid transition there. And this is sort of your boundary layer theory picks this all up and gives you different physics here, different physics there, and then your physics out here. So there's these three regions, all with different distinguishing limits for the physics. So that's kind of a way to start thinking about this. And you can see that this has a really interesting structure because you can get a lot of different behaviors. And here, you know, I don't just have a single boundary layer, I have two, right? And that just popped right out because that b of x was 0 here, and then it was negative everywhere else. Okay? Let's do one more example of this to show you one other thing that can happen. And that is when you have internal boundary layers. So I'm going to show you a case in which the boundary layer doesn't occur at the edge, it occurs just in the middle of the domain. So here's the example I want to consider. And this is on the domain -1 to 1. X goes from -1 to 1. There's the boundary conditions. Here's my differential equation, epsilon uxx, 2x ux, and then 1 plus x squared u. And notice our actual boundary layer, b of x, is right there. It's 2x. And it is 0 when x equals to 0. So in the domain, b of x is equal to 0 in the middle of that domain. And that's exactly what's going to create the problem in generating a boundary layer in the middle of our domain. So let's go about solving it. So let's talk about the outer solution. The outer solution, again, you simply expand in a regular perturbation expansion, and the outer solution then drops out the second derivative, and you get just first order derivative, and this is your governing equations. 2x u naught x plus 1 plus x squared u naught equals to 0. And the solution is given by this. U naught x is equal to, you have x to the -½ and with a Gaussian. Okay? So you can solve this problem and you have your outer solution. But here's what's kind of interesting about this. Let's talk about boundary conditions. It turns out we're going to get a boundary layer at x equals to 0. So in the middle of this domain, there's a boundary layer. So I'm going to have an outer solution to the left and to the right of the boundary layer. So I'm going to have an outer solution to the left, which is I just take that solution I wrote down. Here it is. And that's in a domain, let's say -1 to minus delta. And I'm going to boundary layer on the right, outer solution on the right, which is from delta to 1. So here it is, here. Okay? So those are my solutions that I have with some unknown constants that I can use to satisfy the boundary conditions. Okay? Now what about the inner solution? I already told you that b of x, where b of x equals to 0, this is a problematic spot. And that's one way to understand where could a possible boundary layer be. Just look to see where does b of x, where does it become 0? And that's usually going to be a candidate for a boundary layer. So we're going to expand near x equals to 0. Again, c is equal to x over delta. We're going to expand that region. I don't know what delta is, but we first have to find that distinguishing limit to get us the delta, and then we can find a solution. So here's the rescaled version of the equation, and then you start playing with the balances. Is epsilon a lot bigger than delta? Is epsilon a lot smaller than delta? Is epsilon the same size as delta? What's the relation between the two of them to give me solutions that can match to the outer solution, can satisfy any other constraints I have in the problem? So the dominant balance here turns out to be essentially when you make delta equal to epsilon 1/2, which is going to make this term here be 1. It's going to balance with this term here, and then you also have a one term from over here. This is going to be the distinguished limit of interest. Again, you can play around with this and show that if you don't pick this distinguished limit, you get inconsistencies. You can't match. Solutions go to infinity. Okay? So this is the only one where everything works. It's self-consistent. So here's the dominant balance. There it is. This is the governing equation. Now that I have the distinguished limit right, I can write down this equation and produce solutions for it. In fact, the solutions to this Okay, if I rescale it, I can actually make a transformation from these variables and rewrite this as the following. Okay, so u0 can be written as w satisfying this equation here, and this equation here actually has solution, what are called the parabolic cylinder functions. So these are special functions. They're written as d to the minus 1/2 and c, and d to the minus 1/2 minus c and plus c. So these are two linearly independent solutions. And so yes, they're a little more complicated to work with because they are a special function, but still, those are the two linearly independent solutions for this problem. And so now what you would do is you'd say, okay, I have the solution. And so what I want to do is then say I have two outer solutions that have to match this inner solution, and then I have to match it then on the left and the right, which is going to give me what A and B are. Okay? And the outer solutions already satisfy the boundary conditions on the right and the left. So when after lots of algebra, here's what you end up getting. Your uniform solution is the two outer solutions plus the inner solution minus the two matches. And you do lots of algebra, and here's what you find for those as you do that algebra. So your solution is you get this e to the minus x squared over 2 epsilon, e to the 1 minus x squared over 2 epsilon, and then you get these parabolic cylinder functions that are there as well, which actually specify what happens with the boundary layer near x equals to 0. It's an internal boundary layer. So let me just plot this for you. So this is what the solution looks like. Your boundary layer happened in the middle of the domain. You have an outer solution here. You have an outer solution here. Both are well behaved. You can calculate them. This internal layer are parabolic cylinder functions that you've picked them so that they can match to that outer solution on this side, this outer solution on this side. And that is exactly the structure of your dynamic. So there's this region in the middle where essentially the physics is different in here than it is outside of here, all because that b of x went to 0 there. And so then you have to rescale and get a new dominant balance there. But this is kind of the way you would construct this. So overall then, what I've shown you here with this boundary layer theory is, you can get one boundary layer on the left or the right. We showed how to do that, at least when the case when b of x is either just positive or negative for second order equations. If b of x goes to 0 somewhere, you get some very interesting dynamics. You can get two boundary layers, one on the left and right. You can get a boundary layer I just showed you now, which is in the middle of the domain. And if b of x is even more complicated, you could get boundary layers on both sides and internally. So it all depends on how complicated this b of x is and where it goes to 0, because those are exactly the points in which you get this the dominant balance changes, and so you have to accommodate for that because it's going to create an internal layer there or a boundary layer there that you have to account for in your overall solution strategy. Okay, so I'm going to end there with our boundary layer theory. Really interesting stuff. And again, this is not just pie in the sky. This is really practical, and these kind of effects of boundary layer theory do show up in many physical systems, especially fluid flows, where you get boundary regions, boundary flows that have very different physics than elsewhere in the domain, and part of how you capture some of that is doing exactly this kind of boundary layer theory we're showing here.